Introduction of structures can be defined as forms or shapes such as building, bridges, dams, and walls, and are designed to resist any applied load without losing their own strain capacities and any appreciable deformation, transmit all applied loads to the support systems, and all structure is required to be strong, stable, and functioning. Types of structures can be categorized into mass types and frame types. Frame structure resist the applied loads by virtue of their geometry, while mass structure are a type of structures which are able to resist the applied load by virtue of their own weight. So we have here the example of structural elements. First, we have the beam, column, arc, walls, trusses, and foundation. So we have here the beam structure, column structure, wall structure, arcs, and structure elements. So these are the types of structures. And we have types of joints in frame structures. First, stiff joint, considered have fixity at the point of connection and it is rigid. One member meeting at the joint has an effect on the other member, while pinned joint, also known as hinge point, common applications, roof trusses and bridges were constructed using pin joint, allow relative movement of the member and it cannot resist bending movement. So we have here the types of support in a frame structure. First, pin or hinge, and we have here the reaction. So we have the unknown reactions are number of unknown or degree of freedom, we have 2, and we have horizontal reaction and vertical reaction. And the other support, it is a ruler, and this is the symbol of a ruler, and we have number of unknown 1, and the reaction is at horizontal. Next, we have a fixed support, and this is the symbol, and we have 3 unknowns. We have the vertical reactions, horizontal reactions, and a moment. Next, cables and arcs. First, cables are applied as structural elements in suspension bridges, transmission lines, aerial tramways, guy wires for high towers, and arcs are structures composed of curvilinear members resting on supports. They are used for large span structures such as airplane hangars and long span bridges. And we have the fundamental characteristic of cable and arc. For the cables, they carry applied loads and develop mostly tensile stresses. Loads are applied through hangers. Cables near the end supporting structures experience bending moments and shear forces. And for the arcs, it carry applied loads and develop mainly in plane compressive stresses. And loads applied through ribs, arc sections near the rib sections or rib supports, and arcs other than 3 hinge arcs experience bending moments and shear forces. And we have here the example for a cable type structures. We have suspension roof, suspension bridges, cable cars, guy lines, transmission lines. And in this picture, we have the self-anchored suspension bridge, and this is for a cable type structure. While arc type structures, we have arcs, domes, shells, vaults, and this is one of the example of a dome structure or an arc type structures. For analysis, assume concentrated vertical loads on given vertical lines. So we have here P1, P2, P3. These are vertical loads and it is a concentrated loads at a certain point, which is C1, C2, and C3. And the weight of cable is negligible. Cable is flexible. Resistance to bending is small. Portions of cable between successive loads may be treated as two force members. and wish to determine shape of cable, vertical distance from support A to each load point. And we consider entire cable as free body. Slopes of cable at point A and B are not known. We have two reaction components required at each support. At point A, we have two reactions, A of X and A of Y, or vertical reactions and horizontal reactions at point A. And at point B, we have two reactions, horizontal reactions B of X and vertical reactions B of Y. So we have four unknowns are involved and three equations of equilibrium are not sufficient to determine the reactions. Three equations of equilibrium composed of summation of moment, summation of forces along x, and summation of forces along y, and equate that to 0. And for additional equation, it is obtained by considering equilibrium of portion of cable AD, and we cut AD, and assuming that coordinates of point D on the cable are known. The additional equation is summation of moment at point D and equate that to 0. And we have two equations. We have two unknowns, which is A of Y and A of X. And for other points on cable, summation of moment at C sub 2 is equal to 0 with a yield distance Y sub 2. And summation of forces along x is equal to 0. Summation of forces along y is equal to 0. And yield, we have the tension along x and tension along y. And we have t of x is equals to t of cosine theta, and it is equal to a of x, which is a constant. Example: a cable supports two concentrated loads at point B and C. Determine the sag at point B, the tension in the cable, and the length of the cable. So we have two supports at point A and point D. Three cables or member AB, BC, and CD. And we need to find the sag at point B. So we need to find the distance A to B. This is the sag YB. And we have reaction. We have reaction at point A. We have A sub Y. And we have A sub X. While at point D, we have upward. We have D sub Y. And to the right, we have D sub X. First, we need to find the values for the reaction. And for the first step, you need to use the summation at point A, or summation of moment at point A, and equate that to 0. And clockwise direction is positive and counterclockwise direction is negative value. We have at point A, so the values for A sub Y and A sub X are equal to 0 because the distance is 0. And at point B, we have a load of 100 kilonewton and a distance from B to A, which is 2 meters. So we have 100 kilonewton and then multiplied by the distance of 2 meters, and the direction is clockwise direction to point A. So this is positive. Next, from point B, we have point C and we have 80 kilonewton, and the direction is also clockwise direction, and the distance from C to A, horizontal distance, it is 2 plus 8 or 10 meters, or plus 80 kilonewton, and the distance is 2 plus 8 or 10 meters. And then at point D, we have D of X and we have the distance 0 because point A and point D are in the same level. So D of X times 0 is also equal to 0. And we have D sub Y and the direction is counterclockwise, and this is negative, so negative d sub y. And the distance from D to A, we have 3 meters, 8 plus 2 or 10 plus 3 or 13 meters. And equate that to 0. And the value for dy or d sub y, we have 100 times 2, 200 plus 80 times 10 or 800. So 200 plus 800, that's 1000. And we divide by 13, and the value is 76.92, and it is in kilonewton, and the direction is upward direction. So we have d sub y. And after that, we need to solve using the summation of forces along y and equate that to 0. So all forces along y, you sum up and equate that to 0. So we have a sub y, which is the unknown, next, and the direction is positive, so therefore it's plus. And point B, we have 100 and the direction is downward, so negative 100. Point C, we have downward, which is 80 or negative 80. Next, d sub y, which is upward, and the value for d sub y is equal to 76.92, so positive 76.92, and equate that to 0. And the value for a sub y, we have 180 negative plus 76.92, and the value for a sub y, it is equivalent to 103.08, and it is in kilonewton, and the direction is positive, so therefore it is upward direction. So we have d sub y and a sub y, the values for reaction. If we cut at point C, in this point, summation of moment at point C, we have a of sub y, a of x, which is the unknown, and we have the tension value of equivalent to TCD. And at point C, the value for TCD is equal to 0. A sub y, which the value is 103.08, and the unknown a sub x, a sub y, or 103.8 multiplied by the distance from A to C, which is 2 plus 8 or 10. Next, and the direction is positive, which is clockwise direction, and a sub x is counterclockwise to C. This will be negative a of x, and the distance from A to C vertical is equivalent to 10 meters, and then multiplied by 10 meters. Point B, which is 100 kilonewton, and the direction is counterclockwise to C, and the distance is 8 meters, so negative of 100 times 8 meters. And at point C, we have 80 kilonewton, however the distance is 0. At the same time, T sub CD is also 0, and equate that to 0. The value for A sub x is equal to 103.08 times 10, it's 1030.8, minus 100 times 8 or negative 800, and then we divide by 10. The value for a sub x is equal to 23.08, and it is in kilonewton, and the direction is to the left. The value for a sub x, therefore the summation of forces along x is equal to 0, and we have two x's, or the forces along x. We have a sub x and d sub x. So a sub x minus plus d sub x, and equate that to 0, or d sub x is equal to a sub x, and The value for d sub x is also 23.08 kilonewton, and the direction is to the right. And this is d sub x. Next, we need to cut at point B. So we have, this is, we have point A sub y, which is equivalent to 103.08, and A sub x, which is equivalent to 23.08 kilonewton. Next, at point B, 100 kilonewton. And for BC, we have tension, and this is TBC. Y sub B up to this point is equal to 2 meters. Summation of moment at point B, this B. Summation of moment at point B is equated to 0, positive value, counterclockwise direction. We have A sub x, which is counterclockwise direction to B. We have negative 23.08, and the distance is y sub B. Next, we have A sub y, which is 103.08, and the direction to B is clockwise direction, and the distance is 2 meters. So we have 103.08 times 2, 100 kilonewton, and TBC are all equal to 0 because the distance is at point B is also, or value is 0, and equate that to 0. So therefore y sub B, or the sag at point B, is equal to 8.93 meters. So we have the sag at point B, which is equivalent to 8.93 meters. Next, let's find the values for the tension in every cable. So we have 3 cables. We have A, B, BC, and CD. A sub y and A sub x. And this is point A. And for the point B, we have the values for the AB component, AB of y, or sub y, and AB of x. And summation of forces along y is equal to 0. So we have A sub y, which is equivalent to 103.08, A sub x, and the value for A sub x is equal to 23.08. So summation of forces along y, we have 103.08 and positive value, and we have A sub, or AB sub y, and downward direction we have negative ABY is equal to 0, and the value for AB sub y is equal to, or also, 103.8 kilonewton. Next, summation of forces along x, and equate that to 0. So we have A sub x, which is 23.08, and the direction is negative. So we have negative 23.08, and then we have AB sub x, and the direction is positive. So plus AB of x is equal to 0, and AB of x is equal to 23.08 kilonewton. We need to find the value for TAB. Using Pythagorean theorem, T of AB is equal to the square root of the square of ABX and plus the square of ABY. So we have AB of x squared plus AB of y squared. And we have AB of x, which is equivalent to 23.08 square root of 23.08 squared plus the value for AB sub y, which is 103.08 squared, and the value for TAB, or the tension of cable AB, which is 105.63 kilonewton, and it is in tension. At C, so the diagram, that's to D, and we have the reactions dy, and this is d of x, and we have the load, which is equivalent to 80 kilonewton, and the components of tension BC. And the components for TBC, we have BC of y and BC of x. So forces summation of forces along y is equal to 0. So we have forces 80 kilonewton, BCy, and dy. And the value for d sub y is equal to 76.92, and the value for dx is equal to 23.08. So summation of forces along y, we have BCy, the unknown, so BC of sub y positive minus downward 80 kilonewton, and we have d sub y positive, which is 76.92, so positive 76.92, and equate that to 0. And the value for BC sub y is equal to 3.08 kilonewton, and it is upward direction. Next, summation of forces along x is equal to 0. So summation of all forces along x, we have BC of x and dx, or the reaction dx. We have BC of x negative and positive d of x, which is 23.08, and equate that to 0, and the value for BC of x is equal to also 23.08 kilonewton, and the direction is to the left. So we have now BC of y and BC of x, the components for TBC, and using Pythagorean theorem, we have TBC is equal to the square root of BC of x squared plus BC of y squared, and substitute, so square root of BC of x, that's 23.08 squared, plus BC of y, which is 3.08 squared, and the value for TBC is equal to 23.28 kilonewton, and it is in tension. So we have now the value for BC, which is 23.28, the value for AB, which is 103.63. Next, we have CD. At point D, or in the support D, we have d of y and d of x. The value for d sub x, or d sub y, we have 76.92, and the value for d sub x, that's 23.08, and this is in tension DC. And the components for tension DC, we have DC of y and dc of x. Summation of forces along y is equal to 0. So dy and dcy, and the value for dy is 76.692 positive, and dcy is negative dcy, and minus dcy is equal to 0. So dc sub y is equal to 76.92 kilonewton, and it is upward or downward direction. Next, summation of forces along x is equal to 0. So we have dc of x minus, and dx is equal to 23.08 positive plus 23.08, and equate that to 0. So dc of x is equal to 23.08 kilonewton, and direction is to the right. And the tension for DC cable DC, using Pythagorean theorem, we have dc of x squared plus dc of y squared. The value for dc of x, we have 23.08 squared plus dc of y, which is 76.92 squared, and TDC, the value for TDC is equivalent to 80.31 kilonewton, and it is in tension.